Recall the Rayleigh criterion for resolving two objects that are very close together. It depends on the angle between them, the wavelength of light, and the diameter d of the aperture or lens. Now this angle is really just a relationship between the distance between the objects and the distance to the objects. So let's call them s for between the objects and f for the distance from lens to objects. Now we can actually use this relationship and derive a new expression for Rayleigh's criterion, which will depend on these distances using the small angle approximation. Now s is our dependent variable that describes how small of a distance or objects can be for them to be seen distinctly. Now what can we change about our microscope system to have the smallest possible s, or the smallest distance between objects we can see? Well, here we want a small distance between the objects f, we want a small wavelength of light, and we want a big lens d. Well, how can we decrease the wavelength of light even more? Recall that light has different wavelengths in different media. So if we increase the index of refraction, we can get a smaller wavelength of light. Accordingly, in modern microscopes, we tend to use oil to get wavelengths even smaller for better resolving power. Now let's define the numerical aperture to be n oil, which we'll submerge our system in, times sine alpha, with alpha just being that angle there. Now, this quantity encompasses everything we just talked about. It takes into account all of this information by including the angle, size d, and n. Now, we can show that by plugging in this definition, we can come up with a new relationship that relates s to numerical aperture and the type of light we use. So if we want things that are really small to be able to be resolved, we want a big numerical aperture, which means really, really close to our lens with a high index of refraction using oil, and have really, really low wavelengths of light.